Welcome to one more video on linear integrated circuits. So we shall now discuss the DAC, which is part number 4. So we'll look at one more example to get the confidence on INL and DNL. So we have a graph indicating how does the output voltage is changing. So for 000 input voltage, the output voltage is 0. So that's why INL is 0. For 001, the output voltage was supposed to be 1 by 8. We are getting slightly more than that, so it is half LSB more, so that's why it is half INL. For 010, the output is as per the expectation, that's why there is no INL. For 011 also, the output is as per the expected, so that's why there is no INL. And for 100, we have the output voltage 1 LSB less, so that's why it is minus 1. For 101, for the input voltage 101, the output is as per the expectation, so that's why there is no INL. Whereas for 110 input, the output voltage is 1.5 LSB down, so that's why it is minus 1.5. For 111, the output is as per the expectation, so that's why there is no INL. So let us have a look at DNL. Now output is as per the expectation, that's why there is no DNL. Here with this as the reference output voltage for the previous bit. So for one increment in the input by 1 LSB, the output would have been here. Since the output is more than the desired value, so it is half LSB up than the desired, so that's why it is half LSB. And from here, this would have been 1 LSB up for the next bit, so it was supposed to be over here. So since it is it was supposed to be here, so but it is less than that by half LSB, so that's why it is minus half LSB. With this as the reference output for the next bit, it is supposed to be here, it is there only, so that's why there is no DNL. For 100 input voltage, the output voltage would have been over here, but it is less by 1 LSB, so that's why it is for 100 DNL is minus 1. So with this as the previous output, if there is 1 bit increment in the input voltage, the output would have been over here. So but the output is 1 LSB up. So this is the previous output. The next output would have been here, but since it is over here, the DNL is plus 1 LSB. So for 101, it is plus 1 LSB. And with this as the reference, the output would have been here, but it is less than the desired output by 1.5 LSB. So that's why it is minus 1.5. And with this as the previous output, we expected the output to be over here. So which is this is the output what we have for 110. We expected this to be over here, but the output is actually over here. It is 1.5 LSB. So 1.5 LSB up than the desired one. So this is with this as the previous one, the desired output would have been over here, but the actual output is 1.5 LSB up. So that's why DNL is 1.5. So looking at the DNL values, you can see the DNL value is certainly reduced, and it is almost same as the previous value, but it is not reduced by 1.5 LSB. So that's why you can see the DNL is 0, half, minus, so the next one. So it is half, minus half, 0, minus 1, 1. So this output we still call it as monotonous, because the output is not going below, not more than minus 1.5 LSB. So that's why here the DNL is this output is still a monotonous output. So let us consider the next example. Carefully observe. I think now you are in a position to carefully look at the INL and DNL values. Have a look at this DNL, which is minus 2 here. So for 010, I have this as 010. With this as the previous output, the actual output would have been over here. This is somewhere between, okay, this is between 2 by 8 to 3 by 8. It would have been 2.58, but it is over here. It is 0.5 by 8. So the amount of variation from the expected value and the actual output is minus 2 LSB. So that's why we call such type of output where the output voltage is less than the previous by more than minus 1.5 LSB as a non-monotonous output. So this particular example in which we have the output voltage less than the previous value by more than minus 1.5 LSB, which is minus 2 LSB, we call this particular output voltage as a non-monotonous output. Now we shall see what is some examples of digital to analog conversion techniques. So one of the technique is weighted resistors DAC. So now this is the actual circuit how we can realize a digital to analog converter. As you know, the digital to analog converter takes the digital input and gives the analog output. See here, the digital inputs will actually make this switch on or off. So this is the MSB switch, this is the LSB switch, and we have a reference voltage and there are resistors connected. Have a look at the resistor. This is 2R, 4R, 8R, 24NR. The weight of the resistor is increasing as per the binary value. So this is like this is 2 power 1, this is 2 power 2, this is 2 power 3, this is 2 power n. So likewise, so for B1 is like 2 power 1, this is 2 power 2, 2 power 3. This is the MSB, next MSB, and this is keep on reducing. The output, this is connected to the the inverting amplifier using an op-amp. This RF and these resistors, one of the resistor, the effective resistance will become the R. So we shall see the working of this particular circuit. The output voltage is given by minus RF by R into V reference multiplied by B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus so on so terms. So depending on the number of bits you have, and the last term is Bn 2 to the power of minus n. We shall take a particular example and try to identify how does the this circuit works. Now let us consider a 3-bit DAC. So as you can see, it is 3-bit DAC. We have B1, B2, B3. There is a reference voltage. The resistors connected are 2R, 4R and 8R, only 3 bits. We know that the output voltage is given by minus I0 into RF, where I0 is given by, this is the current that is flowing over here, which is I0, which is again the combination of this current, this plus this. Since the bit is 100, only this particular switch is closed, these two switches are open. So when these two switches are open, now these two resistors are not coming to picture. This entire circuit reduces to a very simple circuit like this. Now you can see we have a V reference, so there is only 2R connected here. These two resistors are open, that's why it's not connected. We have something like this as a circuit diagram. Now can we see now, this is a inverting amplifier with the input voltage as V reference and the resistors are RF and 2R. So if you can actually write the output expression for this one, it is minus V reference into RF by 2R. So that's what is the output voltage. So depending on which switch is turned on, depending on the logic condition, if it is 1 it is turned on, if it is 0 it is turned off. So let us see one more example where we have all the 3 switches turned on. So we have R1, this B1, B2, B3, all the 3 are on, meaning that this is on, this is also on, as well as this is also on. When 3 resistors are on, we are going to have this I0 current due to this arm of the resistance, this arm as well as this arm. So that's why I0 is the combination of all the 3 currents. One is due to V reference by 2R, which is the current flowing through this 2R resistance, and there is one more current which is flowing through 4R, which is V reference by 4R. This is V reference by 8R. So we have all the 3 resistors contributing to the I0. So I0 can be written as V reference. You can take it out by taking it outside. You can write it as 1 over 2R plus 1 over 4R plus 1 over 8R. Okay, you can further write this by taking R as common factor as V reference by R is equal to 1 by 2 plus 1 by 4 plus 1 by 8, which can be further written as so and so. Now you can see we have this output expression, which is minus V reference into RF by R multiplied by 2 power minus 1 plus 2 power minus 2 plus 2 power minus 3. This is exactly like writing B1, B2, B3. Since B1, B2, B3, all the three are 1, 1, 1, we have included all the terms. Whichever term is 0, we can just neglect that, we can make it 0, we get the corresponding output voltage. Now, it is very clearly evident that depending on the bit positions, bit values, that is B1, B2, B3, we're going to have different voltages. So that's why the output voltage purely depends on the bit values, that is B1, B2 and B3. It is very important to note that the resistance values are varying as per the bit position. So if the bit is MSB, we have the least resistance. If the bit is LSB, we have the highest resistance. So we shall see a few more examples in the coming videos.